Hi everyone, welcome to another class on the course of Quantum Theory of Many-Body Systems in Condensed Matter here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias, and in today's class we're going to cover the Schrieffer-Wolff transformation and talk about the Kondo model. So this class is essentially a continuation of the previous class on the Anderson model where we did the mean field approach. And now we're going to do a projection or a canonical transformation that essentially projects the model into the singly occupied subspace of the Hilbert space. And this transformation was done by Bob Schrieffer and Wolff back in the 60s, and it's a very important paper. It's called the Schrieffer-Wolff transformation, and introduces the Kondo model in a very interesting way, coming out of the Kondo model, so of the Anderson model. So we're going to freeze the charge fluctuations in the Anderson model, and then we get the Kondo model, which is essentially a magnetic impurity model, a magnetic impurity in a metal. So let's go right in and see how we can do that. Right, so let's recap the Anderson impurity model that we discussed in the last class. If you missed the last class, I'll try to put a link here. Remember to put a link there. So the Anderson model describes a magnetic impurity or impurity level, which has an interaction U restricted to the level region. So we describe, say, a magnetic atom with a partially filled D level, for instance, where there's an energy cost to add a second electron in there. So you add a first electron, there's the level energy epsilon 0, but if you want to double occupy the level, you have to pay a price of a Coulomb electrostatic repulsion U. Other than that, is very similar to the resonant level model, which we discussed in the other class, in a previous class, where you have these metallic electrons here, a band, here assuming discrete levels, but it could be generalized to a continuum of levels labeled by K here. But and there is a coupling term that allows for electrons from the band to go into the impurity and vice versa. Okay, so there's these two contributions here. And the important part for today's class is that this coupling term is linear in this coupling, and will change the number of electrons in the impurity, right? Because it's either creating or destroying an electron there, while keeping the total number of electrons of the whole system constant. But in today's class, we're going to try to suppress this term and try to look at a regime where these processes, or this T is small, say related as compared to U, for instance. And so one other point is that the impurity has essentially three charge states. There are four, but two of them are degenerate, which we also discussed in the previous class. But let's just do a quick reminder of what these impurity charge states are. All right, so this is the impurity Hamiltonian, right? Has this number operator here times epsilon 0, which is the energy of the level, and this U term and D up and D down, meaning that if I have 0 electrons in impurity, right, total occupation equals 0, the total energy is 0, there's nothing there. Now, I can occupy this impurity with 1 electron. So ND sigma, sum over sigma is 1. So I have either ND up equals 1 or ND down equals 1. So this is then twice degenerate, because here I can have either up or down occupied. So there are two states here with the same energy, epsilon 0. And now there's the other one where if I want to occupy this with 2 impurities, then the total occupation is 2, but the energy is not just 2 epsilon 0. I'm actually requiring an energy cost of U in order to put this extra this extra particle. So this is it comes from the repulsion, the electrostatic repulsion between these particles. That's what this is modeling. Notice that this is quartic in the operator, so this is a two-body term. So it's really an interaction. Now, the interesting part, and in today's class we're going to focus on this subspace where the impurity is singly occupied. Why? Because here I have this idea of a single magnetic moment here at impurity, kind of coupled to the band, but if I suppress the charge transfer, this magnetic moment will simply stay there. And now in this case, for instance, if epsilon 0 is below the Fermi energy of the metallic electrons, this will be the favored configuration for the impurity. In particular, if you are at each 0 negative, which, remember, 0 is the Fermi energy at the leads. I think I forgot to mention this in the previous slide, but this, I'm calling this the 0 energy. And if ED equals minus U over 2, this is a special point, since this is going to be the even in atomic level, this would be the lowest energy state, so the ground state for the impurity. Epsilon 0 equals minus U over 2, and then 0 and 2 epsilon 0 plus U, which is either 0 or 2 minus U over 2 times 2, that's minus U, plus U equals 0. So these two states will be sitting at energy equals 0. So these will be the excitations over the ground state, and these excitations, it's the same energy whether to remove the energy, the particle from here, or to add another particle. It is the same energy. So that's what we call the particle hole symmetry point, meaning that it doesn't matter whether you add a hole, meaning take this electron out, or add a particle, meaning that you're double occupying the state, the energy for these two excitations is the same. Now, what we're going to do today is do a projection in this subspace using the Schrieffer-Wolff transformation. And this is what we want. We want to essentially focus on this subspace and assume that these other excitations are far in energy, so that the relevant physics happens here at this subspace. So in order to do this projection into the singly occupied impurity state, or in the subspace of the many-body Hamiltonian where this impurity is singly occupied, we do the so-called Schrieffer-Wolff transformation. And so the goal here is to find a canonical transformation that essentially will eliminate the terms in the Hamiltonian that are linear with the coupling. So why? Well, these terms which are linear in the coupling, say even this one, for instance, it changes tends to change the number of electrons in the impurity, right? It essentially either destroys or creates an electron in the impurity and creates or destroys an electron in the bath. So if you eliminate these, you only have either 0 or second order process in TK, so then the impurity number will remain unchanged up to second order, right? Because here at second order there will be a process where the electron tunnels in and out of the impurity, so it leaves the occupation of the impurity unchanged. So the task is to find such a canonical transformation, meaning I need to find an operator S such that if I do this unitary transformation, e to the is times h times e to the minus is, the end result is to remove this term and only keep terms which are in order tk or tk square. Okay, and this was done in this famous paper by Schrieffer-Wolff back in the 1960s, where they did find such a transformation. They did find an S which obeys this this condition, and it turns out that if you choose S this way, an S plus plus an S minus, with S plus being the complex conjugate of S minus, and S minus times I is given by this, K, sum over K sigma Tk star. Notice that this is precisely the term in the coupling Hamiltonian, Tk star times Ck dagger sigma Cd sigma. If you remember, way up there in the Anderson model, oh, there you go, right, this term. Of course, you have the complex conjugate of that would be the what we're calling here S plus. Okay, so let's go back to the slide on the Schrieffer-Wolff transformation. One more. Yeah, there. But you have the whole thing here. This whole thing here where E2 and E1 are the energies that I showed in the previous slide of the singly occupied state, impurity state, and the doubly occupied. So this is epsilon 0, epsilon 2, epsilon 0 plus U. So this is minus epsilon 0 plus U. And this is 0, this is epsilon 0, this would be epsilon 0. So why do I need this in order for this to work? So let's take a look on how this would work. And at the end, the end result is that HS will have just the impurity term projecting the SND equals 1 subspace, the band term, and a second order coupling term, which is given by HS2. So let's see how this works. All right, so the idea is then to find this transformation. And notice that S has to be first order in T, right? First order in Tk. So what would be the effect of this this transformation up to second order, or at least in first order I want to eliminate AGA coupling, right? So if I approximate e to the is equals 1 plus is, e minus is equals 1 minus is, I get e to the is, then the h imp plus h band plus h coupling, e minus is, and up to second order I would get this, right? This would be, there would be of course h, which is the sum here, plus which other terms are first order, and this is of course also order Tk. So anything that is s times h coupling is already second order. Okay, so I want to kill the linear terms. So let's just see what are the zero and linear terms here. So I would get is h minus I hs, and the other terms would be s square order of t square. But even here I already have a term that is of order t square, which is s times h coupling. So I would need to do something like that. Is h imp plus h band minus the same thing, minus h imp plus h band times s, which is just the commutator, and all the other terms would, yes, all the other terms would be of order t squared. So here there's one term which is linear in t, and here this term is also linear in t because s is linear in t. So I get h band plus h impurity plus the linear terms, which is h coupling, and here is just a commutator of s and h imp plus h band. Okay, yeah, let's put a round bracket here, and all the rest are t squared. So what I want to impose that this thing has to be 0. Needs to be 0. So that I only keep, I kill all my terms that have linear terms in the coupling. So that means that I need an s to be h imp plus of h band. The commutator, this commutator has to be minus h coupling. That's a condition for s. Then what Schrieffer and Wolff showed is that if I find s to be written as s equals s plus s minus, with s minus given by that, that's precisely does the trick. And one thing that we can do is try to calculate, or at least see how this commutator can be equal to minus h coupling. All right, so let's try to do that in a bit. Okay, so what we're going to do is, again, try to calculate the commutator of is minus with hm plus h band. So first, let's divide the is minus into two terms. One is what I'm calling is minus 1, which is this one. Notice the nd, this is a sigma bar. And the other is is minus 2, which is 1 minus nd sigma bar, and here the denominator is different as well. So let's see what happens when I calculate the commutator of this one with h imp, and let's see what we get. So here I have a sum over k, sum over sigma, tk star, then I have nd sigma bar, epsilon k, epsilon 1 is, epsilon 2 is 2, epsilon 0, epsilon plus u, epsilon 1 is epsilon 0, so this is minus epsilon 0 plus u, okay? And then I have this ck dagger sigma, cd sigma, applied to h imp, and h imp is, all right, sigma prime here, and d sigma prime, or sorry, there is also an epsilon 0, and d sigma prime, plus u and d, so this is all multiplying, right? And d up and d down. Okay? All right. So let's remind ourselves of some important results here. Oh, and this, of course, has minus the opposite, right? H, okay, maybe this is cutting, so this should be minus h imp is minus 1. Okay, but we're just going to flip this whole thing over here, and we're going to cancel this guy. All right, so the first thing is to look at is this guy here. He's going to be this will commute essentially. There's no CK or CK dagger here, so I'm worried about this one. This one, well, not gonna do much. Number operators usually commute, and yeah, in this case they will commute, but this one doesn't, right? Here and here. So let's remind ourselves what was the rule here. So if you have CD sigma apply to n d sigma prime, okay, this is delta sigma sigma prime CD sigma prime plus ND sigma prime CD sigma. Okay, so the commutator of this and sigma prime is delta sigma prime CD sigma prime. Okay, this is, we derive that. Well, you can do it yourself. You might want to convince yourself that ND sigma prime and D sigma equals, or D or anything here, ND sigma and D sigma prime. All right, this is also, yeah, you might enter things like that, but they will have opposite signs, these terms, and they will cancel. So something that you should remember. The other thing that you will need later on, but we can already right now, is that if you have the dagger, say CK dagger sigma and K sigma prime, this has a minus sign. Okay, delta K, let's put a K prime here, K prime C K prime sigma prime plus and K prime sigma prime CK sigma. All right, so these three should carry. All right, so with this three we can already see that when I apply CD sigma to ND sigma prime, I'll get a delta CD sigma prime here. Here it will be something else, and then this we already calculated. If you have CD sigma and the sigma and the sigma bar, this is simply ND sigma bar times CD sigma, okay, plus CD sigma. So if you apply this to there, you can easily, after some calculations, come to the conclusion that this commutator will give you essentially this coupling, sorry, will give you a sum over K and sigma, and there will be a TK square here, epsilon K minus epsilon 0 plus U, and what is going to happen here is an ND sigma bar, still there, there's going to be a ck sigma, and there's going to be a, now something like this, epsilon 0 cd sigma plus u nd sigma bar cd sigma. Okay, so keep that in mind. Now if you do the other one, the s-2, and you try to do then, or let's do still S1 but with H band. So still this one with H band. So let me pause a bit. I'm going to copy this over and put a S band there. Just a sec. Okay. And this times H band, which is going to be K prime, sigma prime, epsilon K prime, and K prime, sigma prime. Okay. Minus H band IS1 minus. Okay. So if you apply now the same operators that we had before, this same commutators here, can encourage you to do this calculation. This will give you this. Some calculations later will give you sigma k, still tk here. There's still going to be, and there's going to be nd sigma. There's going to be a minus epsilon k, and there's going to be ck dagger cd sigma, and here is going to be epsilon k minus epsilon 0, which is it should be plus epsilon 0. Oh no, I'm doing this one. Okay, no, yeah, epsilon 0 plus u. Yeah, it's still the same. Sorry. Okay, let's do this real quick. Minus. Yeah, it has to be the same denominator. Right, so this minus sign comes from this guy, right, the ck dagger here. Okay. And now if I add this guy and this one, if I have this, I have is minus 1 H band plus H impurity, I'll get minus sum of k. There's going to be a tk star here. Now notice one thing that's important. Here I'll have nd sigma bar times nd sigma bar, and nd sigma bar square equals nd sigma bar. Okay, this is important. Other than that, I'll have here nd epsilon naught plus u. So I'll have the epsilon naught plus u here. And here there's a minus epsilon naught plus u, so I'll have this. I'll still have all that, and the sigma bar, ck dagger cd. So there I'll have all this commute, so can put n bar and d will just have the nd square there, so it's fine. I'll have E0 plus U. There will be minus this H E epsilon k here, ck sigma, and there's going to be in the denominator a epsilon k minus epsilon 0 plus U. So this will give me minus 1. And you know, already looks quite similar to what we want, right? Well, no, sorry, there's the minus sign here. The minus sign comes from there. So this is minus sum over k sigma k star. There's this nd bar here, ck cd sigma. Okay, but it's very close to what we want. Okay, maybe you're not reading this. Let me just copy this over here. All right. Okay. Now, if I do, the only thing that's missing is now to do the commutator of this guy with H band plus H amp. So if I do that and also try it at home, if I do, I did it in my notes here, S minus 2 H band plus H amp, something great to do on a Saturday afternoon, right? What I'm gonna get is minus TK star, but instead of this guy, I'm gonna get 1 minus ND, okay? CK sigma CD sigma, which is precisely this. Why it comes? Because you have this 1 minus here, but all the rest is pretty much the same. So you can see where this is going. So when I add these two up, I get what I want, which is IS minus H band plus H imp equals minus sum over K sigma TK star C sigma CD. Now, it's not too far-fetched to imagine that if I get S plus here, right, which is minus IS minus, I would get, sorry, this S minus, so I would get band plus H amp equals minus the complex conjugate of this. This should be a minus. Yeah, well, you get a minus here, right? So if I take the complex conjugate of this, will be H band commutator with minus IS minus dagger, which is S plus, and I take the minus again and invert the whole thing. I should get this TK CD CK sigma, and the sum is IS. Oh, let's do underneath. So if I add them up now, again, I'll get IS H band plus H imp equals precisely minus H coupling, which is what we want, and that's a beautiful result that was derived by Schrieffer-Wolff back in 1966. So let's go back to the slide. So the last step is to write the second order terms of GS. So we show that the first order terms vanishes by this choice. Now we have to write the second order terms. And it turns out that this term leads to the so-called Kondo Hamiltonian. Okay, so how do we write this up to second order in the couplings? We notice that the first order vanishes. So what do? We expand these exponentials. Oops, sorry. We expand these exponentials up to second order in S. Right? So this is minus IS, and here there's minus S squared, and this there is minus IS, 1 minus, oh, this is plus, this is minus S squared. So what do we get here? EIS H E minus IS equals, let's put it this way, plus IS H minus S squared H 1 minus IS minus S squared. Okay, so when I do that, and I want to keep all the terms up to first order in the coupling TK. Okay, that's this term right there. All right, so there's going to be this term H. There's of course going to be this term, the commutator of S and H, and there will be a couple more terms which we'll write. There's going to be oh, sorry, there's a 1/2 here, 1/2, yeah, yeah. So there's going to be terms like this. First term is going to be minus 1/2 of S squared H plus H S squared, right? Coming from this and from this. And there's going to be a term which is also quadratic in S, which is going to be minus plus, or well, let's see, plus there is going to be 1i minus I, which is going to be this with this, plus I S H S. Okay, and this is going to be plus, and I'm going to write this as this, I commutator of S and H, and here is going to be something interesting, which would be the commutator of S and S again. And all the other terms are going to be order cube or something. How do I get this? Oh, notice the commutator of S and H is S times the commutator minus H S minus the commutator times S. And this is S squared H minus SHS minus SHS plus HS squared, or SH plus HS squared minus 2 as is SH, and 1/2 of that is precisely what I have there. Okay, so now we have to count the orders because there's t's inside H here. So we know that this, I have the H imp plus H band plus H coupling. But this will essentially cancel. Here I'll have the IS H imp plus H band, which is first order, and these two will cancel, remember, right? By definition, we found the S, but there's going to be an ISH coupling here, okay? And the only one term here that is quadratic in T is when this, I have only H imp and H band here. So this is going to be minus 1/2 commutator of S and H imp plus H band, which we know has to be, so the commutator has to be minus H coupling, so this is minus H coupling. So with an I, right? But the commutator then is minus H coupling over I, so it is plus I, right? If I put minus I here, I'll get a plus I there. Oh, just multiply by I here, or minus I, sorry. Plus I, right? Plus I, of course, has to be. So this, if this is plus H coupling, this is minus I over 2, and then I get the final result that this should be equal to H imp plus H band plus I over 2, so this gives me an IH coupling minus IH coupling 2, I over 2, SH coupling. So this is HS, second order in H, okay? I over 2. Now, then we have to go back and calculate all those commutators as we did before. I'm not going to do it, but the result is precisely what I have in the slide that I'll show you now. All right, so if you calculate the commutator of S and H coupling, you get multiplied by I over 2, and you get something like this, where you have two types of terms. One that's going to be something that will involve CK dagger and CK prime, okay? And this term, well, what are the prefactors here? So remember, everything is order of t squared. So this coupling, it essentially, involves all these energies. You can do the math. So this does not involve impurity operators, right? They factor out. So this is just a charge scattering term that only refers to the band electrons, so it has nothing to do with impurity. All right, so it just, in a sense, renormalizes the energies, if you want, right? It's like if you add this, is like a non-diagonal part in the band Hamiltonian. So no big deal. The important thing is this one. This one is also quadratic in the t's, okay, and has these two contributions you can calculate, and depends on u, right? If u equals 0, this thing will be 0. That's the first point. Now, it involves these mixings of spins in the dot operators and in the band operators as well. And these tau's are Pauli matrices. I is x and y and z. So this is like a spin operator. It's a way to express a spin operator in terms of creation and destruction operators, like fermionic creation and destruction operators. So this is like a spin scattering term. What it means is that I have a state k coming in and being scattered to a state k with a different spin. So there will be a spin scattering here. And the dot will also change its spin state as a result of this scattering. So if you actually do the calculation and express this in terms of the SZ components of the spin, it's like a spin flipping scattering term that will include different combinations of incoming k electrons and outgoing k electrons with opposite spins. For instance, think of the z component of the Pauli matrix, which inverts the spin, right? So here, yes, it will connect up. Oh, sorry, this should be 1 here. There's a typo. This should there will be off diagonal terms. So the z ones is like a diagonal term, but there will be off diagonal ones which will lead to spin scattering terms here in these terms. And this is important as it will lead to the so-called Kondo effect that hopefully we'll discuss next class or the class after that, probably the class after that, when we discuss the transport in the Anderson model. And we'll look at what these spin scattering terms will do. Essentially, they'll be the leading contribution at low temperatures. And again, this comes from the many-body interaction U. So this is, the Kondo effect will be a many-body term. So the end result is that we did a Schrieffer-Wolff transformation, and here, that thing that we're mentioning, that in that ND equals 1 subspace, the impurity looks like a localized moment, it appears right here, right? So and this will have consequences. In this Hamiltonian, the charge degrees of freedom of the impurity are frozen, so we're always at the ND equals 1 substate, and that gives rise to this spin scattering term and after the Kondo effect. One last comment is that we talked about the mean field approximation, and there's always this question of, okay, is there a way to capture all this physics, not only as perturbative expansions in T as we did here, or at mean field, but say in all orders of T, and say that we can even all orders of U as well? And the answer is yes. There's one technique called the numerical renormalization group technique, and hopefully I'll discuss it a little bit in the class where we talk about transport in the Anderson model. And this technique is able to kind of bridge I was going to say renormalization group flow, but let me put it in another way. It tends to bridge the perturbative approaches from small u to small t, because these are two very different limits, okay? So we're going to discuss that, and this is a technique that was developed in the 70s, and it was very, very important in understanding the low energy physics of the Anderson Hamiltonian. Okay, that's it for this class. See you next class. Bye-bye.